Gravity, a fundamental force that governs our universe, has intrigued scientists for centuries. Today, we delve into Einstein's theory of gravity and how it improved upon Newton's work. Newton visualized gravity as an invisible force pulling objects together. His laws beautifully explain the motion of planets and apples alike, but they stumbled when it came to the extremes, like the gravity near black holes or the bending of light. Enter Einstein with his general theory of relativity, a game-changer that redefined our understanding of gravity. Instead of viewing gravity as a force, Einstein portrayed it as a curvature in space-time caused by mass and energy. His theory not only filled the gaps left by Newton, but also predicted mind-boggling phenomena such as light deflection and time dilation. So buckle up and get ready to unravel the mysteries of gravity and the cosmos with Einstein's revolutionary perspective. Einstein's theory of gravity took a revolutionary turn from Newton's concept. He proposed gravity as a curvature of space-time itself. Let's imagine space-time as a vast trampoline. Now place a bowling ball in the center. Notice how the bowling ball causes a dip or a curve in the trampoline surface. This is analogous to how massive objects like stars and planets warp the fabric of space-time around them. Then, let's introduce a few marbles onto the trampoline. Naturally, they roll towards the bowling ball, but why? It's not due to some invisible force pulling them. Instead, they're merely following the curve that the bowling ball are stand-in for a massive object created in the trampoline, or in our broader analogy, space-time. This perspective is a significant departure from Newton's force at a distance concept. Newton viewed gravity as an invisible force that acts between two objects, no matter how far apart they are. But Einstein proposed a different perspective. According to him, gravity isn't a force per se. Instead, it's the curvature of space-time caused by massive objects that make other objects move towards them. This means that when a planet orbits a star, it's not being pulled by the star. Instead, it's moving along the curved path created in space-time by the star's mass. The planet isn't falling towards the star, it's following the straightest path in a curved space-time. This shift in perspective is profound. It changes how we understand the universe and the nature of gravity itself. We can now see gravity as an inherent property of space-time, shaped by the mass and energy of the universe's objects. This new lens also allows us to explain phenomena that Newton's theory couldn't, such as the bending of light around massive objects and the slowing down of time near these objects. But that's a story for another time. Einstein's theory thus changed the way we perceive gravity, not as a force but as a result of the warping of space-time. While Newton's law serves well for everyday objects and planetary motion, it stumbles near extremely strong gravitational fields. Here's where Einstein's theory steps in. Ever tried calculating the trajectory of a marble rolling down a hill? Newton's law of gravity could help you out beautifully, but let's take this marble on a cosmic journey, say, near a supermassive black hole. Suddenly, the calculations don't add up. The trajectory deviates, the marble doesn't behave as predicted. It's like Newton's law has its blindfold on when dealing with these astronomical giants. The culprit? Newton visualized gravity as a force acting at a distance. A pretty solid concept, until you reach the extreme edges of the universe where normal rules just don't apply. Near massive stars, near black holes, the gravitational fields are so strong, so intense that Newton's law begins to falter. And then stepping onto the stage, we have Albert Einstein with his general theory of relativity. He proposed a radical idea. Rather than seeing gravity as a force, Einstein visualized it as a curvature in space-time created by massive objects. Picture a bowling ball on a trampoline creating a dip. Now imagine a marble rolling on the trampoline. It doesn't roll in a straight line but follows the curve created by the bowling ball. That's Einstein's view of gravity. Objects moving along the curves in space-time created by massive bodies. This idea, this new vision of gravity, answered the quirks that Newton's law couldn't explain. Near strong gravitational fields, Einstein's theory predicted the way objects would move with remarkable accuracy. It made sense of the chaotic dance of stars around black holes. It predicted the minute shifts in Mercury's orbit that Newton's law couldn't account for. So while Newton's law of gravity is a fantastic tool for most situations, when you're dealing with the heavyweights of the universe, it's Einstein you need in your corner. Einstein's theory of gravity therefore holds the upper hand when dealing with strong gravity fields. Einstein's theory of gravity also explained phenomena that left scientists puzzled under Newtonian gravity, such as the bending of light and time dilation. Let's delve into these fascinating concepts. In the realm of Newtonian physics, light was considered to travel in a straight line and time was constant. But Einstein's theory of relativity turned these notions on their heads. Imagine light as a traveler journeying through the universe. According to Einstein, when this traveler, our light, passes near a massive object, it doesn't continue on a straight path. Instead, it follows a curved trajectory, much like a car veering around a bend. This is known as light deflection or gravitational lensing. It's as if the mass of the object is bending the very fabric of space-time, causing light to curve along with it. But what about time dilation? Well, let's say you have two clocks, one here on Earth and the other near a black hole. If you could compare them, you'd notice something strange. The clock near the black hole would tick slower compared to the one on Earth. This slowing down of time in a stronger gravitational field is known as time dilation. Einstein's theory suggests that gravity isn't just a force acting upon objects, but a warping of space-time itself. The stronger the gravity, the greater the warping, and hence the greater the light deflection and time dilation. These phenomena weren't mere theoretical predictions. They've been confirmed by numerous experiments and observations. For instance, during a total solar eclipse in 1919, British physicist Arthur Eddington observed starlight bending as it passed near the Sun, just as Einstein's theory predicted. Similarly, time dilation has been confirmed by comparing the ticking of clocks at different altitudes. Clocks at higher altitudes, where gravity is slightly weaker, tick faster than those at sea level. These phenomena further testify to the robustness and depth of Einstein's theory over Newton's. With its ability to explain these and other phenomena, Einstein's theory of relativity has revolutionized our understanding of gravity and the very fabric of the universe itself. Einstein's genius was not about overthrowing existing theories, but building upon them. Let's look at the scientists who influenced him. The work of two Dutch physicists, Henry Lorentz and Hendrik Antoon Lorentz, played a significant role in shaping Einstein's perspective. These two scientists' contributions to the field of electromagnetism, particularly the Lorentz transformations, were instrumental in laying the groundwork for Einstein's theory of special relativity. The Lorentz transformations describe how the space and time coordinates of an event change under transformations between two different frames of reference, which are moving at a constant speed relative to each other. This concept was vital in Einstein's development of his theory, as it demonstrated how measurements of various physical phenomena differ for observers in different frames of reference. Essentially, it opened up a whole new way of looking at space and time, and consequently at gravity. Another significant influence on Einstein was James Clerk Maxwell, a Scottish physicist known for his profound contributions to the field of electromagnetism. Maxwell's unification of electricity and magnetism into a single theory of electromagnetism was a major inspiration for Einstein. The idea of unifying disparate physical phenomena under a single theoretical framework appealed to Einstein and influenced his approach to understanding gravity. Einstein's theory of general relativity, which describes gravity as the curvature of space-time, was not a spontaneous revelation. It was the result of Einstein's deep understanding of the work of these scientists and his ability to build upon their insights. Einstein's theory, therefore, is a testament to the cumulative wisdom of many great minds. It's a perfect example of how science progresses, not in isolation, but as a collaborative effort, with each scientist standing on the shoulders of those who came before them, reaching for a more comprehensive understanding of our universe. Einstein's theory, therefore, is a testament to the cumulative wisdom of many great minds. Einstein's theory of gravity, while building on Newton's work, provided a more comprehensive understanding of the universe. In this journey, we've delved into the depths of gravity, from the curvature of space-time to the intriguing phenomena of light deflection and time dilation. We've seen how Einstein's theories, while revolutionary, did not completely displace Newton's. The laws Newton formulated still hold their ground in everyday situations and many astronomical calculations. But when we venture into strong gravity fields or explore phenomena like the bending of light or the dilation of time, it's Einstein's theories that come to our aid. It's a testament to the beauty of physics, where new theories don't necessarily invalidate the old, but rather build upon them, leading us to a more profound understanding of our universe. So join us again as we continue to explore the fascinating world of physics, where new discoveries always await. Don't forget to like, subscribe, share, and hit the notification bell for more exciting content. This is created by artificial intelligence, so please excuse any mistakes in the script and irrelevant media. Your feedback is always appreciated.